Okay, so I want to talk about cognitive abstraction. And the question here is why abstraction and how abstraction? So I think that the question of why abstraction in terms of functionality or computationally is pretty clear. If you want to be able to use information that we have from some sources and use them in another situation, then if we take everything that we have and we abstract general ideas and then we apply them to a new situation, that's a great way to do transfer and analogies and learning in one areas and understanding in another. So this is really kind of, I think, is a very basic mechanism for generalization and for learning over a long time. So what I would like to talk is about a possible way that the brain is doing this kind of abstraction. And this is a joint work with Patrick Taylor. He was a postdoc of mine, and now he's assistant professor. So the question that I'm going to ask is, can we find a general symbolic hierarchy or aggregation of hierarchy in the brain? So there are two inspirations that make us think that they may be. One is the visual hierarchy that everybody knows, starting from lines, more and more complex objects. So we know that in the visual stream there is a hierarchy, and perhaps there are also in the auditory and the olfactory region there are kind of a demonstration that there seems to be also a hierarchy. Also, when we talk about deep neural networks, they have also some properties of hierarchies similar to the one that are seen in the visual stream. So the question is, do we have the same type of things for symbols or for thoughts? So in order to answer that, we looked at Fmri databases, and in particular, we looked at the particular large databases that collected many experiments. And as you all know, the idea of these databases is they ask people to do some particular action or cognitive task, like to add two numbers or to move their fingers or to do something. And while during this activity, there is this Fmri that is taken. So there is the cognitive tasks and the Fmri. And we kind of ask ourselves, can we try to look at the different cognitive behaviors and the many, many experiments and find some mechanism or some kind of reverse engineering, some idea of perhaps why for particular cognitive action we have particular activity in the brain. So that's kind of the question, and let me first tell you the results, because you never know when they stop you, and especially that I'm standing between us and the coffee break. So we'll start from the result, and then we'll go to see how much we have. So the results are as following. We find that there are actually three interrelated hierarchy. So the first one is a cognitive hierarchy of brain regions. We'll kind of define how we can define hierarchy, and this hierarchy will be related to the input cortices. So this is one. The second one will be behavioral hierarchy, whether some behaviors are aggregation or above or higher level than other behaviors. And the third one will be aggregation of representation and abstraction in the brain. And the main point will be to show that all these three hierarchies are related. So the connectome hierarchy of brain region will be related to behavioral hierarchy, which will be related to representation hierarchy. And once we have everything together, we'll suggest that we have similar way to what we have in the visual stream, but also for symbols, also for notions, ideas, and cognition. Okay, for the results? Okay, so let's see how we show that. So I cannot, there is no talk without Turing N. So this is really a little thing. But actually in the break, Christoph van Malsburg said the same thing, that you need to have lots of sensors in order to try to see how you get intelligence. Okay, so let's start with the first one. How do we look at connectome hierarchy of regions? So it's kind of a strange idea because clearly the brain and cortex is very, very recurrent. And we all know that. So what's the meaning of saying that there is actually a hierarchy in the brain? Because hierarchy kind of implies something like feed-forward connection, which is not the case. So the notion of hierarchy that I'm using is the distance from input cortices. So if we have like a deep neural network, so on the left side we'll have with dark things that are close to the input, and I will have it in less and less dark, kind of going lighter as I get to farther places from the input. So let's do the same exercise with ROI, okay, with brain regions. So let's say that we'll take here the visual cortex, and we'll take the visual cortex and color it with very dark blue. And then we look with a resting state fMRI and DTI and see what's the next area that is lighting off and what's the next area that is lighting off. And when we do that, we'll actually cover the whole brain with different colors, and these colors will tell us how long it takes for, if you activate the visual area and you're waiting, what will be coming next and what will be coming next. So it's kind of give you a flow of information. So this is what will kind of start with thinking about how we can create distances from the beginning, and that's why we have on the top of it this deep neural network that we can now think that it starts with the visual cortex and then go in until we're very far away. But there is really no reason to think about only visual cortex because we have all kind of sensory primary cortices. So we can think about all this list. And if we think about all these lists for each of them, we can take the brain and color it when the very dark blue is in the cortex, in this particular, let's say, olfactory area. Well, olfactory is kind of interesting. So auditory area, and then we're going away from that. So we can do that for each sensory area differently. So each of them is a whole coloring of the brain by blue, where the dark started from the input cortex, and you went away with the distance. With distance is from the timing of activity. And then we can actually take all these, just a moment, sorry, I'm going to the wrong direction, and then we can take all this that we have here and averaged it. So why averaging? So averaging will give us something that will say I'm as far from all the input modalities at the same time. Okay, so now when we average it together, we'll have this one coloring of the brain where the dark blue will be all the sensory cortices, and from there will be what is next affected by all of them, and the next, and the next, and that's how we go farther and farther from the input, and we'll ask what's happened when we're getting farther and farther from the input. So here, that's what we get. So we get a picture like that, and this is a coloring of the brain by its connectome, and then we already see that there is something very interesting in this particular hierarchy. If we take this coloring and we cut it arbitrary to 10 different colors, and each color will have the same amount of neurons that are together. So if we have, so it's about 80 million neurons per bin. So if we have these 10 bins where 10 is kind of arbitrary, taken in B1, which is the closest to these cortices, we have the insula and these areas that are related to basic awareness, basic consciousness. If we go all the way to half of our hierarchy, going away from the inputs, we're going to our fifth bin, and it includes the hippocampus and MTL, and actually the celebrity neurons. So you all know the celebrity neurons are those that were shown to be kind of higher level in the sense that they have distance from all sensory input, because you can think of the same person by hearing the voice or seeing a picture or reading the name. So for us, this is half of the hierarchy, exactly half. And as we continue all the way to the areas which are farthest from all inputs, according to this temporal activity, then we see that we have the frontal pose and the left singular anterior, and these are really the abstract cognitive functions. So what we did so far was just a very simple coloring exercise. We colored by very dark blue the sensory cortices, and we colored by less and less dark, by brighter and brighter, these areas which took longer time to be activated after you activate something from the input sensors. So this is the first hierarchy. This is hierarchy of regions, okay? Now the second hierarchy. So the second hierarchy that I would like to ask, and that's why really we wanted to have the first hierarchy, is my prediction. And my prediction was that if we do this hierarchy, perhaps we'll be able to see activity of brain from fMRI from particular behavior, and it will go on perhaps not to a particular area, but to a particular bin. So we'll be able to say this behavior is going to be 3, or this behavior is going to be 5, and it will tell us how abstract or how far it is from input. So that was the expectation, but I was wrong. And in fact, as we go from all these databases to all these activities, you actually see that for any activities you have, for any behavior, for cognitive behavior, you look where the brain is shining, and in different experiments you put threshold, and the answer is usually that it's above that, that's the relevant part. But in fact, if you add and take average of many experiments from different labs from different times that treated the same cognitive behavior, you see that there is kind of like a mess, because whenever you take a behavior, it does not fall into one bin. So there is no behavior that falls into one bin. And the question was at that stage what to do. Option 1 is to throw this research to the garbage. Option 2 is to try to find something else. So we chose the something else, and this is something that is as simple, that is almost stupid, but is very interesting. So we started looking, okay, so if we look at many experiments of finger tapping, so if you're looking there in the databases, you see that there are many experiments, and you see that there oops, wrong direction. Okay, there are many experiments. You see here the number of experiments that are related to finger tapping. Okay, so we took all these experiments and we added them all together. So what does it mean to add together? If there was some activity for in one brain, then we added the second and the third and all the 1,000 different experiments that were done. So we have lots of activity. Why do we do that? That's the power of large numbers, because it's possible that in one lab something were different, but when we take many experiments that did pretty much the same, we have the power of large numbers, we have something that we can trust. And then we look what happened. We take all this addition and we ask how many regions are falling into the first bin. And the answer is this. And how many to the second bin, the third bin, fourth, fifth, and this way we look how much of the activity is falling into each bin. And then we do something that is very embarrassing to mathematicians, but is okay for biologists, and we do linear regression. And what we find is just a line that kind of tell you what's happened with this activity. So with this activity, we can say that there is much more activity in bin 1, much less activity in bin 10, and if we put a line, there is a particular negative slope. Interestingly, if we continue to another activity, which is reasoning, and we again add all the 976 cases that appear in the database from different labs in different years, we add them, and then we take all the points on this additive brain, and we now project it again to the different bins, where the bins are the distances from the input, from the sensory inputs. We see that there is some activity in B1, some in B2, and some activity in bin 10. And again, we do these horrible things as putting a linear regression and looking, and we have a positive slope. Okay, so you see that the slope is not exactly a description, but it's a first order kind of description. So what we did then is kind of a fun thing. If you look on the left side, you see that the gray picture is the way really to go over the data. So the data really was doing something like that for a particular behavior, but then we do the regression and receive a slope, and the slope can be anything from negative and positive. And then we took all the behaviors and put them in the order from the most negative slope to the most positive slope. So if we go this direction, we see that we start with whistling and video games. These are the video games that I tell my son that if he plays a lot of them, he will be able only to whistle and play with his fingers. But I think nowadays they're kind of smarter video games, but I still hate them. Okay, so we start with video games and chewing. You see the level of video games. And then you go to writing and eating and going to go and no-go and deductive reasoning, and all the way here to encoding and reward task, delay discounting task, and all the way to naming. So anybody here was in a Hebrew school or in a Sunday school? So I don't know if you remember, Adam was in paradise, in Eden, in the Garden of Eden, and his job was to name the animals. So according to that, that's kind of the most hard or the farther from input activity. Okay, so this is a second hierarchy. So the first hierarchy was that we just took all the areas based on Connectome, and we say which areas are closest in activity flow to the input, which are the farthest. Then we see there is something interesting about behavior, which makes it that it's not that behaviors go directly to particular area, because all behavior can appear all over in the brain and in all kind of distances. But the interesting part is that there's some activities that appear more at the beginning and less at the end, and some activities that appear more at the end and less at the beginning. Okay, so this number, this slope, is telling you where this behavior appearing. Now, when you look at that, I think you start kind of wondering if this is related to abstraction, just because it looks like that. But this is not good enough to make a decision. So what we did is the first thing, we just took every time a small subset of fake activities, and we had a mechanical Turk survey where we gave 1/4 to people that will take 6 activities after we explained to them what aggregation and abstraction means, and they were supposed to put it in some order. We put all these orders together, and we found very, very small p-value, which means that the order of the order that people organize these activities happen to be very similar, almost the same, like the slope that we found to them. So what does it all mean? It means that the brain has some very interesting way of organizing things, so that any activity that you do, or any cognitive activity that you do, appears in some way closer, in some ways farther. And this is actually the representation of this activity. And you can see that as the activities or the thoughts become more and more abstract, they become farther and farther away in how much they activate farther areas rather than small areas. So this is kind of a brain property, and it's interesting by itself. So together with a grad student, Alex Gain, what we're trying to do is to take this property. So this is not a regular hierarchy, this is kind of a hierarchy of slopes. We try to take this hierarchy of slopes and see what it tells us about neural networks. Can it tell us how much abstraction there is? Can we use it into the learning algorithm in order to actually move representation, to have this possibility of abstraction? And once we have that kind of abstraction, it can be used to having analogies in a better way. So that's kind of the current work that we do. So we kind of reached all the way to the point of trying to explain these hierarchies that in brain structure, and now the next point is to transfer them to neural network. There are some other people that suggested various directions that one could take. Like if we have this kind of hierarchies, is it related that there's some relation to similar behaviors, Or do people mature and the abstraction change? Like perhaps there are some activities that are more related to abstraction and then become more related to input or differently as things change. Or perhaps you can take it and suggest that there are some diseases because things that should be in particular slopes appearing in a totally different slope. So, oops, I have lots of unrelated things. And with this, I want to close this talk about abstraction. So abstraction, I think, is just one property that you want to have in a smart system, an intelligent system that can do analogies. And I just kind of want to go back in a before I finish this talk, because this is kind of opportunity to all of you. So if you guys are working in different facets that are related to systems that can have lifelong learning properties because they do abstraction, because they do analogies, because they learn to represent in a particular way, because they have self-reflection, or because all kind of ideas, we have actually these group meetings that are meeting every so often. And if you have interest to come and demonstrate your work and perhaps find people to collaborate on continuing that, then we have a tool for that, which we call the Center Group for Lifelong Learning. So I just wanted kind of to bring it up. So like the abstraction is like one example, but there are many, many mechanisms that we'll want to see how perhaps brain does them or how nature does them, and then to see whether we can take them and put them into system to get them doing better. So thank you very much.